All right, so welcome to class 5. So we're going to cover, we'll do some recap from last time. We'll cover the CNN or convolutional neural networks. We'll have some application of CNN for denoising. And if we have time, we'll cover some transfer learning part 1 today. So going back to last class, we had some questions about different things, and I selected a few questions that in general kind of represent all the questions that were asked. So first one from Saeed is, when should we train the model for longer versus add another attribute to help in the classification? So when you are training, and as long as your loss is going down, you can keep training. You can keep training for longer. You can even slow down the learning rate a little bit so that it goes slower and is more smooth. And I think as long as the loss is going down and the validation loss keeps up with it, you're good to train for longer. And you can add another attribute, but adding another attribute, if you have a larger system, it's an expensive proposition because you have to then go through the entire pipeline and set it up again. So you want to select features early on well, so that you don't have to go through that process again. Next question from Ricardo is the latent representation always smaller? It doesn't have to be. So in any network, I think we can treat any hidden layer as a latent representation of some kind. So when we did our first neural network in predicting home prices, the input was only 8 features or 8-dimensional. So, but we had 32 node network in the middle as a hidden layer. So in that case, we are expanding the latent representation. So anything in between the input and the output, you can treat it as a latent representation of your input. So that's totally fine. So we don't have to worry about whether it's bigger or smaller. In case of autoencoder, it necessarily goes smaller because that's what we are trying to do. So that's just the structure of the network. Another question from somebody anonymous, would it make sense to have lossless image compression? So in general, yes. So you want to have lossless image compression so that you can send the image and somebody can recover it without any loss. But due to the nature of the neural networks, you cannot have a lossless image compression fully. And then many of the general formats like JPEG, they are not lossless. PNG is, but JPEG is not. But you still get pretty decent quality of compression. And you wouldn't use an autoencoder for compressing images in general because the JPEG and the PNG, they are very fine-tuned to have very good compression for images specifically. Next question, does TensorFlow have some tools for making new examples by translating pixels of existing ones? That's a good question. So in the brief example that I showed just before the class ended last time was how to take the data and add noise to it. And I'll go over that in detail today. So we can do that ourselves. We can take images and do modifications to pixels, but there are also some tools that allow you to do that. And I'll cover some of them later on. Next question from Alberto, is TensorFlow better suited for computer graphics, machine learning tasks? The TensorFlow is just a tool set, right? So what you do with it is up to you. Any kind of computer graphics stuff necessarily deals with images, and you can use pretty much any toolkit for that. So TensorFlow is something that we are using because it is a little bit easier to use. It has the support for Colab. We can do this online learning, but you can use Caffe or Torch or any other thing that works. So they should all work in a similar way, different API, different quirks about each of them, but they should all be good. Next question from Patrick is, how do we retrieve the compressed data instead of the prediction from the network? So that's a great question. So at any given point in the network, after you have trained, you can retrieve a layer and its weights. And we'll do some of that when we do variational and autoencoders later on. But yeah, the whole network is available to you. It's just an API thing. You can call methods on layers to get their names and their inputs and outputs and the weights that have accumulated there. And then you can create a different model that just has those two layers, like input layer and the compressed layer that you want. And then you can predict on that. So that way you will get the compressed image out. So that's a great question, and that is one way we use to kind of see what is going on in the network in the middle, because sometimes it's pretty ambiguous or not clear what is going on. You only get the input and the output, but there are ways to kind of tap into the middle layers and find out what is going on. And you can reconstruct the weights and the inputs in some way that it looks similar to an image. So these things are not images. In the middle layer, there is some latent representation that may not be an image, but you can kind of force yourself to restructure it in terms of an image and at least see what might be going on. So it's not a great picture, but it at least gives you some idea of what is going on. All right, so those were the questions we had. I hope that answered some of your queries, and then let's move ahead with the CNN. So now we're getting into some of the complex architectures, and this is where we use state-of-the-art stuff where we can do something practical. For now, until now, we had dealt with toy examples like MNIST database or the home prices, and those are standard introductory data sets. And now we can get into something really cool. So CNN, what they are and how do they work? So CNNs are something that have been modeled after the human visual cortex, where when you look at something and without changing your eye positions, you're only seeing part of the view. And as you move your eyes, you have different receptors in the eye that kind of click, and there are overlapping fields of views. So as you move your eyes, the entire picture of your field of view appears as one picture, but all the receptors in your eye, they're not firing at the same time. The different receptors are designed to fire at different things. There are rods and cones which fire more about the color or the periphery, black and white areas. So there are different receptors that act in different ways. They kind of act as filters, but they're overlapping. So as a whole, you see in your field of view a large image that is kind of consistent with your worldview. So CNNs are kind of modeled after that. The way they work is you take an input image, and instead of connecting all the features or all the pixels into the next layer of the network, you do some operation on it. So by doing that particular operation, you are averaging some pixels in your image and thereby reducing the number of nodes in the next layer. So that's the idea. And what are those operations? So we want to do something that kind of captures the sense of the image without having to capture every pixel. So it's some kind of an averaging function that you apply. And that particular thing is known as a convolution. So convolution is an operation that is not specific to neural networks. It's been around for a long time. If you've ever done in Photoshop something like edge detection or embossing, and that operates by applying a convolution. So what convolution is, think of it as a filter that takes an area of an image, say 3 by 3 pixels, and applies this filter, the 3 by 3 filter, onto the input image. So you can imagine taking a small area of the image and sliding it around like that, that covers different parts of the image in an overlapping manner. And you take the filter and apply it to the pixel in the image, and thereby you get some average here. So that's the repeated operation that you do. You go along one axis of the image and then a little bit down and then go along again until you cover the entire image and you've filtered the image. So what you get out here is some kind of a representation of an image, which captures the high level features, but it's not as dense as the original image. So that's what you capture out of this. They are called feature maps. And you do this multiple times. And as you do it in between, what you do is you average it out, or you take the maximum of each of those small areas. And that's subsampling, or max pooling is what it's called. And as you go along, your number of maps increases, or number of feature maps, but the size of them decreases. So this has the effect of basically having fewer and fewer nodes as you go along. And in the end, what you do is you put in one fully connected network so that you can get your output. So if you're doing classification, then you would get the number of outputs that you need. And then if you are doing some kind of a prediction of an image, you would expand it out to a full size image again. So that is in a sense how CNNs work. And CNNs are like one of the major building blocks of any kind of image-based neural networks. So very popular, and do lots of different things with it. And we are going to do something similar with it. So let me pause here and see if you have questions, because I introduced a lot of different concepts here. So if you have any questions, let me know. And let me look at the chat for a second. All right, so looks like people are still getting I think access to the files should be available now. And if anybody has questions about what convolution is and how they work. So somebody asked about like, how do you mathematically express this? So everything mathematically in a neural network is essentially matrices, right? So the images are matrices, and you do take dot products and multiply them. So the convolution operation itself can be thought of as a dot product of the small filter that you have, which is going to be a 3x3 filter or a 4x4 filter. And you can take each pixel in your filter, multiply it by the input image pixel, and whatever result you get, you store that. And then you do that for all the, say, 9 pixels in the 3x3 filter, and you get a resulting feature map out of that. All right, so let's see an application of CNN. And last time we covered some data pipeline, but I didn't go into detail. So today we are going to cover that. So open up this file if you have access to it, called denoiser.ipynb. And we are going to do a bunch of things here. So we'll go slow, and I will go step by step and cover all of it. So we are importing some packages as usual. Let's do that. And just like we did last time, we are going to import this data set called UC Merced. And it's a set of satellite pictures. So this is going to take some time because it's a fairly large data set, about 307 megabytes. As it is downloading, we can go ahead and look at some of the code. So this data set we are downloading is in terms of something called TensorFlow dataset. The TensorFlow dataset is a set of data structures in TensorFlow that are highly efficient and that allow you to process your data in a very efficient manner. And this is a great practice because once you start dealing with larger image sizes, your images may not fit in memory at the same time. And TensorFlow dataset allows you to kind of stream those data right from the disk and be as efficient as possible. So when you use TensorFlow datasets, try not to use any Python or NumPy because that slows it down. So you want to keep everything in terms of TensorFlow. So very common operations that are available in NumPy or Pandas, they are also available in TensorFlow. You can use them directly, and you should for the purpose of keeping your data as efficient as possible. So let's look at what we're doing here. Looks like downloading is still going on. Let's let that go. So the preparation of the data is very similar to what we did last time, but because we are dealing with the TensorFlow datasets, there are going to be some quirks about the API and how we do that. It's going to be very similar. So we will take the dataset, which is the training dataset, and it looks like there are 2,100 images in this. It's still going on. All right, let it go. And then hopefully by the time we're done explaining this, it should be downloaded. So we're going to take this full data set that we get out, and we are going to take some of it for training, that is 70%, and keep the rest for testing. So again, 70-30 split. Some people do 80-20. That's totally fine. We can do either. That's not a problem. So as we will see, these images that we are getting from this data set, they are 256 by 256 times 3, one for each RGB component. So that's a fairly big size. We are not going to be able to handle that in an interactive class like that. So what we want to do, and this is good practice in general, is to deal with the smaller patches of images. So this particular function here, both flat map and map, they are similar to the map function in Python, which basically take your input and apply a function to each of those inputs. So it's going to take all these images that are in the training data set, and it's going to apply this extract patches function. So let's see how we extract patches from that. So let's look at the extract patches function. So extract patches function is going to get called for each of the image. So what we are doing here is from the example that we get, we take the image part out. Again, the example itself may have multiple things in it. In this case, each example contains the name of the file and the class that it belongs to and the image itself. So we're taking the image part out of the example, and then we convert the image type because it's an RGB from 0 to 255. We're going to convert that to a floating point number, and this conversion also normalizes it automatically. So we're going to convert it to floating point, and then at the same time, we're going to convert it into the range of 0 to 1. So again, if you look at hover over on this function, it will tell you what it does. So it's taking it, converting it to floating point, and at the same time, converting it to range from 0 to 1 as well. So once we have the image converted into or normalized it, then we are going to extract some patches. So this function called extract patches in TensorFlow library, it takes an image and it extract a patch or multiple patches of these sizes and strides. So again, you can look up the function for details of what these parameters mean. But essentially what we are doing is taking patches of this size, width and height, with a stride of width and height as well. So basically we are, so if our patch width and patch height, we define them somewhere here as 128. So you're going to get a 128 by 128 patch from each image, and you're going to move stride size. So you're going to jump like one patch ahead, and then get that patch. So essentially you're getting 4 patches out of each image. So that's good in 2 ways. First of all, we've reduced the size of the data that we have to deal with. And secondly, we have increased the number of data points that are available to us. So this is another way to do data augmentation where we can get more data than we have available to us. So that's all good. So we get essentially 4 patches. You can change this. You can get more patches out of that. So we are able to do this because the kind of thing we are going to do today is denoising. And denoising is generally distributed evenly around the image. So it doesn't matter if we train on the entire image or if we train on a smaller patch, as long as the thing that you're trying to fix or correct, in this case noise, is kind of randomly distributed around. So that should be okay to do that. In general, you may not be able to train on patches because, say, if you're looking for a specific thing, it may not be generally distributed, so the training may not be as effective. So, but we are able to do that here because of the nature of the problem we have. So once we do that, again, there are some API quirks where we need to reshape things because it's going to return you an array of 4 elements. So we are going to reshape it so that you get the right kind of the array. So that's all okay. Don't worry too much about it. Like, all these things are API quirks. So you have to keep aside like the theory and the intuition and what things are doing versus what the API allows you to do. So these things are just calls that you need to make to fix that, and you get that from experience, from doing this thing or reading the documentation of what is happening. So ultimately, you're going to return a new data set now, which is comprised of patches. So what you put in was 2100 times 0.7, and what you get out is 4 times of that value. So ultimately, after you have executed this, you would get that. So next step we do is, now we have our patches. We don't have ground truth. So because we don't have noisy images, actually we do have the ground truth, we don't have the noisy image part. So we want to create this data where that would act as our input. So what we are going to do is we're going to add noise to these patches. And that would then give us the input data that we need to train this network. So to add noise to a patch, we do another map function, which is going to now take all these patches. So this part is taking the input training data set and creating patches for you, and you get that patches in train_ds. And next, you're going to take those patches and add noise to each patches and assign that again. So let's see what the add noise does. So add noise is again similar. It's getting called for each patch here. What we do is we create a noise shape, which is the same size as the patch. And its mean is 0 and standard deviation is that. So you can change that to make the noise bigger or smaller. So you're using a small amount of noise that we add. And rest of it is just like what is the data format of this noise. We're using floating point everywhere. So that's the call that you use to create a noise pattern. So again, just a random sampling from 0 to 1. So then what we do is we add this noise that we generated to the original patch. And once you get that, you have a noisy patch. But now adding things to something, it may increase its value by more than 1. So what we want to do is clip it. So if it becomes more than 1, we are going to just make it clip this between 0 and 1, because this noise is random. It may generate values that are close to 1, and if you add it to the pixel value, it might increase more than 1. So this is just a clipping so that the values still remain in the range of 0 to 1. So that's what we do to create our noisy patch. And now we are going to return not just the original image, but couple it together with the noisy image. So what you're getting back here is two patches now. One is a noisy patch, and the second one is the original patch. So this will act as input and the ground truth in our case. So noisy would be the input and original would be the ground truth. So, and then we return this as a tuple. That's what add noise does. So once we have that, our data set is prepped. And one thing to remember here is that no operation is happening. All we are doing is setting up the pipeline. So data has not gone through any of this. So that's the good thing about the TensorFlow data pipeline, is that it is exactly what it says. It's a pipeline. No data goes through it until we need it. And when we need it, we can call some methods that will cause it to kind of process the data through the entire pipeline. So it's a good way to set up your entire pipeline as efficiently as possible. And when you need to get data out, you can start doing that. So then we go ahead and do the same thing for the testing data set, except in the testing part, we want to test on entire images, not just patches. So we can use a trick here, and we can do the same kind of thing. So our code looks similar, except in this case, we are going to say we want a 256 by 256 patch, which is the entire image. So that way we are dealing with the full size image in the testing phase. And we add noise again and do the same thing. This is another quirk of how big the batch sizes are. For testing, we are going to use one item per batch. So that all sounds good. And let me answer some questions if we have any. So I'm going to answer live Bobby's question about ray tracing. So the question is about, in ray tracing, is the noise normally distributed? So in ray tracing, we don't have a normally distributed noise. Noise in ray tracing is similar to a camera sensor noise, where the dark regions have more noise because light is not able to get through to the dark areas. So this method, it will still work. It may not work as well for ray trace noise, but it will still clean up a lot of the noise that you get normally. So in ray tracing, you have access to other things like 3D geometry, the normals, or the albedo. So you can take advantage of this additional data in ray tracing and train using that. So that's an advantage you have with ray tracing, because you have access to intermediate results that you can feed, not just the final image or the noisy image. You can take advantage of additional layers as well. Another question I would like to answer is from Patrick Frigg. Are those patches going to overlap? So in our case, they don't overlap because we use the stride size of the same as the patch width and the patch height. So stride is like how big a step you take from one patch to the other. And we are taking a step size that is exactly one patch wide and high. So in our case, these patches don't overlap. But there's no problem if they overlap, because all we are trying to do is get similar patches or similar noise profile patches. And that should be totally fine if we did allow them to overlap. We can make the patch height and patch width smaller as well. So you can get more data augmentation that way. So in this example, I wanted to keep it simple. So our patch height and patch width and the strides are chosen in such a way so that there is no overlap. You get exactly 4 patches per image. All right, so let's continue. So let's take a look at what these things look like. And somebody also asked, like, why are we doing extracting patches in the test data set? That's a good question. So we don't need to. I just wanted to reuse the function that I wrote, and this is an easy way to do it, and then allows me to basically just call the same function twice. Let's look at some of this data after we have extracted the patches and we have denoised it. So before we do that, let's see if our loading has finished. So it looks like it is done. Let's see what the data looks like. Again, we looked at it last time. There are 3 features there. One is the file name, which is a string, image itself, which is RGB components to it of some size, and each of them are in 0 to 255 range as a unit, and each data also has a label, and there are possible 21 labels in this thing. Total examples 2100, and we can extract the image part out by using this. It tells you what the image size are, or the dimensions are. So in this particular code part, we are essentially just taking the data set and just showing some examples from what this data set is about. So again, these are satellite images. These are the first 9 data points from the image set. Pretty high quality, 256 by 256. And then let's just execute these. So these are not going to do anything now, just defining them here. And let's do that, and then prep it for training, prep the testing data set. So now that we have extracted the patches, added noise to them, let's take a look at that. So as I said, nothing is passed through this pipeline until we do some operation. So one of those operations is called take, and take takes a number that gives you the number of examples from the data set. So we can get 5 examples from the data set. This is the point when you call this function, is when input data goes through the pipeline and does all this extraction and stuff. So we're going to shuffle this so we get random numbers, and we're going to plot each of these images. So we're going to plot both the noisy part and the original for each of those patches. So let's see what that looks like. So there you go. So we have this noisy version and the original patch. So these things look a little bit different than what we had here, is because we are taking a patch out of this. So most likely one of the patches came from this image. We got a double scrolling issue. So as you can see, we've managed to add noise to each of these patches. So this would act as our input, and that would act as our ground truth. And we are going to do a comparison after the end of each batch, and then try to minimize that loss. So essentially, that's what our CNN is going to do. And let's see how to do that. So there's one more step. When we create efficient data pipelines, we want to set up our batch sizes up front. So what we are doing is setting a batch size of 32, and we're going to shuffle this and repeat it so that we have infinite supply of data. We can train as much as we want. So when you set up the epoch, in the previous example, you had a limited thing where you can run the data set for the 10 epochs or 20 epochs. And when you use something like this repeat, it is going to give you an infinite supply of data. And as you need it, you are going to get that data. And this particular function called prefetch, it is going to prepare the data asynchronously. So while you are training, you don't have to then go back and get the next batch. it's going to keep it ready for you. So right now we're running on the Google Colab cloud. So the data is all available out there. So if you were running it on a local cluster or on your machine, this comes in pretty handy because the data doesn't even have to be in the memory. So it will get the data if you're doing multiprocessing, if you have multiple GPUs. So all this pipeline behind the scenes, there are like very efficient algorithms and procedures in there that will take care of prefetching your data, preparing it right when you need it. So you can deal with enormous amounts of data, like terabytes of data without any problems. So again, a simple code as that, while we're applying this to an online 2100 image data set, you can deal with the terabytes of data using the same code. And TensorFlow is smart enough to kind of understand what kinds of GPUs you have, what kind of memory you have, and it will create caches for you. It will keep the data as efficient as possible. So it scales up pretty nicely. So all you got to do is add more GPUs or add more memory, and then you can get faster and train better, but it will scale it down to even if you just have a single CPU or a GPU. So that's pretty good. So you don't have to do as much work, because in the beginning days, it was all limited to small amounts of data, small sizes of images. Now you can deal with as much resources that you have available to you. You can then go on the cloud and then on demand get as much processing power or memory that you need if you pay for it. But it's all possible. So this scales up pretty well. So I highly recommend that you use this kind of setup for any kind of real life data. So you can do that. All right, so this is the function that we will use to create the CNN itself. So as I said, in a CNN, there is a convolution that happens, and that you specify using this con2d. That's a convolution layer. So right here we have 3 convolution layers, and this is the number of nodes. This is the filter size that we're going to use for creating our feature maps, and the activation function that you're going to use. And there is some padding and the input shape. So that's all there is to it. So I think all the computation and setup is happening behind the scenes in this particular call, where it sets up both the activation and the filter in the same call for you. So if you hover over here, it will give you more details on what these things are. There are different kinds of parameters that you can use to adjust. Padding is one of the things where you can use different kinds of paddings, because we are going, this filter is going to go along the image in the X direction and the Y direction. And as you go along, when you reach the edges of the image, what do you do there? So do you go past the image, or do you stop? So this padding, basically, there are different kinds of padding available, where if you reach the edge or a corner, then you can duplicate the pixels that you have on the edges, so that when your filter part of the filter is hanging out of the image, it can still work reliably. So different kinds of padding give you different results, but it should be totally fine to use the same padding. So that's the convolution network. And then just to compare the sizes, we are going to use an auto-encoder network, which is of a similar size. So let's print the summary. So in a convolution layer, you'll have this number of parameters. So number of parameters in a convolution network, it's a little bit tricky and hard to tell. It's still a simple mathematical operation. In a fully connected network, it was easy to see because everything is connected to everything. You can just multiply the next layer number of nodes by the previous layer's number of nodes, and you get the number of connections. In a convolution layer, because you are using these operations, the number of parameters, sorry, is a little bit harder to calculate because it also depends on the padding, it depends on the filter size. So I won't go into the details of this, but you can look it up. It's still simple algebra to calculate, but there are too many parameters for us to worry about there. So I won't go into details over here. Suffice it to say that this is our neural network for convolution. And we are going to create our autoencoder with a similar number of parameters and see what that looks like. So even with a simple connection like that, we get a explosion in the number of parameters. So compare this autoencoder with the CNN. So look at the difference in the number of parameters. So it's huge. It's like orders of magnitude difference. So that is why CNN are one of the most popular networks, because they automatically reduce the number of parameters needed and thereby reducing the amount of memory that you need. On the other hand, it's not free. The cost is that the filtering step, the convolution step, is doing a lot of operations. So it's not like in a dense network like an autoencoder, the work is simple. All it's doing is summing up the weights and applying the activation function. So it is much faster. In a convolution, the operations are more complex because you're going along the image and computing these convolutions. So still, the advantage that you get from the reduced number of parameters is huge. That nobody uses autoencoder or a simple fully connected network for any kind of image-based operations. Everybody uses a CNN or some variation of CNN. So again, we're not going to use this, we're going to use the CNN. So let's look at the model and then compile it. So we're going to use the mean average error as our loss here, which is basically just the difference in the pixel value of the input versus the ground truth. And then we are going to train for 10 epochs. So again, we're dealing with large sizes. So this is going to be a little bit slower than what we had done in the past, but it should still be interactive enough for this class. So while it is going on here, let's see if we can use some questions. So I'm going to answer a question from Gabriel Zachman. Can you please comment on the choice of the first parameter of the conv2d function? So that's the number of filters. So if you look at, you just hover over here, because it's working, it won't show. So you can just look at this function, either by hovering on this, or just go to the TensorFlow API. So it's the number of filters that you have. And that's the next parameter is the size of the filter. So another question from Cesar is there a way to, wow, this went over fast. Where did it go? Can I run the notebooks in Windows without install? So let's answer this live. Cesar is asking whether you can run these notebooks in Windows. So that's going to be hard because you can't just run these. These are not pure Python code. They rely on this Jupyter-derived environment, but there is a way to install all the software that you need, and you can do that, and I'll show it to you maybe towards the end of the last lecture on how to create an environment on your personal computer if you want to try these out without being in the Colab environment. It involves installing a lot of software, and because it may conflict the versions that you need with the already installed software on your machine, we still want to be able to use something called a Python virtual environment, which kind of isolates the software from the installed software on your machine. So I'm going to show you how to do that just for people who are interested. If you have a nice RTX machine at home, you want to try these things at home, or if you want to do more fun stuff like hook up your webcam, because we can't hook up a webcam to this Colab environment. We can't do interesting things. We won't be able to do it on your local machine. It's certainly possible, and I'll show you how later. All right. Let's see where it is at. It's still going on epoch 7. So let's just look at the loss. It is going down, so that's a good sign that network is learning and training. So while it is training, let me show you what to do after it has trained. So we are going to predict, obviously. So we can take 3 images from the test data set as our prediction. And let's skip this show results, but let me show you how to predict it. We are going to call predict on it, on the noisy image, right? So each of the batch that you have in the prediction is going to have 2 things in it, a noisy and high res image. We are going to predict on the noisy image, and we get this P image, which is predicted image. And this particular thing, I will go over it in a moment, but essentially what we're going to do is we're going to save these 3 arrays. We're going to have the denoised version and the high-res version all put in this array. So you can compare the results easily. In addition, we are going to output something called SSIM. So SSIM is a measure of how similar 2 images are. It's basically just gives you one number, so you don't have to compare pixel by pixel. So it's used when you have lots of images. You're not going to look at pixel by pixel and to see like what does it mean if there are 90% of the pixels are very similar, but 10% of them are different. Is my image then similar or not? So this SSIM, structural similarity index measure, gives you an idea of how similar 2 images are. So this is built into TensorFlow. It will take 2 images, compare them, and give you one single number. It gives you an idea of how similar the images are. So we'll print that as well. So essentially, you got 3 outputs coming, which is a denoised image, and the high-res image, and the noisy image. So that's what we do in prediction. And then we got to plot these things. So we're going to plot these 3 items: the noisy image, the denoised image, and the ground truth. And then just for fun, we are going to just do a difference between the 2 images. So we're going to use this package which compares 2 images. It's just basically going to do a diff, a visual diff between 2 images. And this is what we're using. And we'll plot that as well, just to look at like what the actual difference between images are. So hopefully this is done by now. So it looks like it's done. And the loss is decreasing, which is good, which means we can train for longer and get even better results. So let's execute this part, get this function ready, and do the prediction. What's going on? So here's the result we got. Looks like we got decent structural similarity out of the 3 images that we predicted. The last one looks not so good. but let's see the results. There you go. So you should have 4 images per data set. So this was the input that we gave, and this was the result of our prediction or denoising that we did. And this is the ground truth. And in the last row, we plotted the difference using SK image. So you can see it works. It is getting better. So it's not as good as the ground truth yet, but it will get there eventually if you train for a longer part. But you can see that you took in the noisy image and then denoised it to a decent level, actually. So it looks pretty nice to me. And as you're going along, you can train for more and get even better results. So one note I want to make about the difference. So if you look at, you can barely see that on my monitor, but you can see parts of here. Sometimes I can't tell whether my monitor is dirty or there is actual data in here. So if you look at the difference, you'll see some visual thing. You can move this window up and down to see what is on your monitor, dirt or actual difference. So there are some differences here that you can see. You can barely see any difference. You can see this diagonal line here. Maybe if I can make it bigger, you can see it better. So you can see a lot of differences here, barely any difference here, some diagonal differences here. If you look at our SSIM, you see that the third image has the lowest SSIM, which is one thing to note about human perception. So the SSIM is a perceptually based metric. And if you look at mathematical difference, there's a lot of differences here in this image, but visually, this is the closer or the cleanest result. So, and whereas in this, there are not many differences, but this is the least similar image to the ground truth. So that's one thing to worry about in image comparison is you don't rely too much on just the mathematical difference. You want to look at it, image as a whole, as a perceptual level to see how similar images are. Because when you're dealing with images in visual effects or animation, people are going to look at the images and react to them. Nobody's going to compare pixel by pixel except the hardcore nerds. So we are more concerned about how people look at images and react to them. All right, so that was denoising, it is one of the fundamental applications of CNN. And as we will go through more of it, we'll see what it means. All right, so next thing we do, now that you've seen denoising, we can do a lot of different things with it. So there is a variation of CNN called UNet, or something called ResNet as well sometimes. It is exactly like a CNN all the way, and then it has some properties of like an autoencoder-like thing where you go all the way down to a small size, and then as you turn around, you can start expanding it back to the original size again. And then with one big difference. That difference is that we are taking some weights from here and putting them here. So you're essentially connecting these levels in a way. So that's the residual part where you're taking some higher level features and connecting them to the upper nodes in this network. So this entire shape is like a U shape. That's why it's called the U-net sometimes, with these residual connections, also known as skip connections sometimes. So that's just a more complicated version of a CNN, but it tends to give much better results. As you can see, you're taking some higher level features and then putting them here, and which means these get promoted up here in the final image as well. So it tends to preserve higher level features much better than a plain CNN. So UNet is also popular, and it works as well. So that's all the time we have today. So I want to, in the next class, what I want to do is build a facial recognition system. So facial recognition is in the news for all the wrong reasons these days, but it's a good application. It's something that we will try to implement. And what I would need from you is to send me a couple of images, images of your face, essentially, two portrait size images in different lighting conditions or different times of your life. And we'll see if we can recognize those. We'll do that as a live experiment in the class next time. So moderators will send you an email address to send these two images in. Again, just a profile picture. In this case, you can imagine this particular face, this region, just a portrait or something. So two images, not too big in size, maybe 100 by 100 is more than enough. So just email them out if you are not too shy about sending your facial images. And we'll try to see if we can do facial recognition live here in the class, and then you'll take away from that a fully working system that you can deploy, hopefully for good. And for the homework, what I want you to do is try other applications of denoising. So once we set up denoising in this way, you can think of other image degradation as denoising. For example, if you have underwater images, they always look kind of foggy. You can clean them up manually, and then you'll have ground truth versus the real image. So you can train those. So you can try different kinds of denoising by doing data augmentation. One good thing to try is to upres an image. And upresing an image would require you to add a function that is, instead of add noise, you would add a function that would create a low-res version of your image. So find a method that creates a low-res version of your image and add it here somewhere. You can call it def, something like down-res. And what you can use for this is basically just resize the image. Resize the image very small, and that would kind of degrade it and then resize it back up to the original size using some kind of a simple filter. And that essentially will degrade it. Do that a few times and it will degrade it even more until all you have is like large pixels. So write a function that similar to add noise that does the down-resing, and then you can then try to up-res an image. So this works really well. It's one of the best applications of CNN, super high-res image from a low-res image, and you can try it out. And if you are ambitious, you can try other things like you can take frames from a video and you can find middle frames. So for every 3 frames, you have the beginning frame, the middle frame, and the end frame, and you can try to predict the middle frame. So that way you can do frame interpolation as well using very similar techniques. So try those 2 examples. Maybe the down-resing is the easier one, and you can do that. The second or third example you can try is something else is saturate. So you can just add more color to the image, and this is going to be really simple. You can just add value to the existing pixel that will saturate it a little bit, and then you try to desaturate the image. using your training. So again, downresing, desaturation, all these things are, you can think of them as generalized denoising or fixing an image degradation. You can also think of cutting out parts of the image. So just add something like a hole. So you can create these random holes in the image, and then you can train that versus the ground truth of the full image, and it will learn to fix those holes. So this is similar to what you would use in Photoshop, for example, to kind of fix patches of images. So you can train for that. So these are kind of in increasing order of difficulty. Maybe the saturate one is the easiest. And you can try these three things if you get time. And send me those images for doing facial recognition next time. And that's all I had for today. And we'll meet again on Friday and do some facial recognition. So thank you, everyone. See you next time.